Okay, hi guys. In this lesson we're going to be talking about moment of inertia calculations. So this is one of the most fundamental parameters or properties which engineers use in their calculations very often, especially structural engineers. And in this lesson I'm going to talk to you about three different things. Number one will be I'll give you an introduction and explain what is the moment of inertia and how is it calculated. I'm then going to show you some free web software that can be used to help calculate this moment of inertia for different section sizes and different beams. And then finally, I'm going to do a deep dive into the theory of these moment of inertia calculations and show you how you can understand them from first principles and do your own hand calculations. So this will be helpful if you're, if you need to do these calculations for work, or if you're a student and need to do them as part of your coursework. So without further ado, what is the moment of inertia? So the moment of inertia is basically a quantity that expresses a body's tendency to resist angular acceleration. So if you imagine you're trying to spin something around, like how does that shape resist against you? So how does the shape make it difficult in order to rotate it? So this is quite important for lots of structural calculations, because quite often you're putting forces and pressures onto different structural elements, and you want to understand how much they're going to rotate or how much they're going to move. And so basically you have different calculations which you can do to actually understand this property, and then use it in other calculations for design. So here you can see some examples of commonly used shapes, things like rectangles, circles, tubes, triangles. And here are some of the properties that we calculated, like cross-sectional area, and also these moment of areas, moment of inertias. So here you can see one for rectangles, one for circles. But what we can actually do is sometimes when we have unusual shapes, sometimes they can be non-symmetrical, or they can be combinations of these shapes put together. So we can actually use some software to help us to design these. So what I'm going to show you here is some free software to help us do that. So if you go over to this website, www.calcforge.com, and open up the moment of inertia calculator, from here I can see basically different categories of shapes. So what we've done here is we've loaded in different section sizes, different standard sections that are used. So universal beams, universal columns, European sections, American sections, and then these hollow sections as well. And what I can do with this is I can actually pick any one of these that I want, and I can select the section size from here. So I can pick one of these standard sections like the 203 section, and I'll see that this display here actually updates with an updated area for this, updated moment of inertia for the X and the Y, and also other properties that need to be used quite often in beam design and column design, like radius of gyration, elastic section modulus. All of these are really useful to structural engineers. One of the really useful things though is that I can actually create custom shapes as well. So quite often if you're doing a design, it might not be a standard section, it might be a custom size section. So with this I can click custom section, and then I can click add rectangle, and I can start to build up a custom section here. So let's say I have this quite thick section at the top here, have quite a thick section at the bottom down here, and then I have a thin section that's sort of connecting between them. You just need to make sure that these actually overlap. The sections all overlap, otherwise you'll have an error. But I can sort of build this up myself into this custom section, which isn't a standard one. I can then hit analyze, and then this software is going to run some maths equations itself, and then it's going to generate this estimate for the moment of inertia about the X axis. So that would be across this axis here, so it's the strong way it's bending, and then this would be across the YY, so this would be like the weak way it's bending, so it's a bending about that axis there. So this software can basically help us with generating these estimates for these key parameters for our designs. But what I'm going to do now is I'm going to show you how you can do these calculations by hand yourself as well. So here we're finding the moment of inertia for composite shapes. So in order to do that, we need to find the centroid of the composite shape. And then we can proceed from there using the parallel axis theorem. So the first thing that we need to do is we need to recognize that this T, this is the cross-section that we know, a T-shaped prismatic member, and we know that the top rectangle is going to have a centroid right in the middle, and the bottom rectangle here is going to have its own little centroid there. And what we want to do is we want to find the overall centroid of the composite shape, and it's going to be somewhere in between them, somewhere about like that. Alright, so the way that we need to do this is let's identify where the centroids are for each of the composite shapes. Let's take our measurements off from the bottom here. So we have a measurement like that, and we also have a measurement like this. So obviously this centroid is going to be half the height, so that's 30. And then this centroid is half that height, so that's 10 millimeters plus 60, so we're up to 70, up to this centroid. Right, so here let's do ourselves a favor, and we'll label this section A, and we'll label this bottom section down here section B. Now the goal is to find the location, or the location which is the distance of the centroid away from the bottom. So the way we're going to do that is we're going to construct a table like this. We did this previously in the previous video, and we'll do it over here again. So we have section A, and then we also have section B. But first we need to figure out the area, and that's the reason we're doing this here. I actually write this equation right here, and this is from the statics video, if you watch those about finding the centroids of the composite shape. So again, the first thing that we need to do is we need to find our areas for each of these areas of section A. So this is 80 millimeters times 20 millimeters. That's going to give us 1,600 millimeters squared, and the area of section B here is 20 millimeters times 60 millimeters, which gives us 1,200 millimeters squared. We're going to have to take the sum of areas here, so if we just sum those up right now, we're going to get 1,600 plus 1,200, which is 2,800 millimeters squared. We're going to be plugging that into our equation at the bottom here. Alright, so then the next column that we're going to need in order to figure out what this equation is we're going to have to take the y bar of each of the composite sections, each of the parts. We'll throw that in. We have the y bar and the capital Y bar for as well. We already figured out that it's from the bottom, so it's 70 millimeters. Y bar for section B, we already figured out that's 30 millimeters. And the last thing we're going to need in order to do this is the equation here. The easiest way to do it is to put the whole row in our table, or a whole column in our table here for y bar. So we can just get 70 millimeters times by 1,600 millimeters. That gives us 112,000 millimeters cubed. And if we do the same thing, we basically get 36,000 millimeters cubed. And if we take the sum of those, the sum of y bar, then we'll see it's 148,000 millimeters cubed. So actually we have, we can fill out the equation now. We have the sum of all of the parts, the product here of y bar, and that's 148,000 millimeters cubed. And the sum of all the areas here, we also have that. That's 2,800 millimeters squared. So if we just divide those, we're going to find that the y bar, the height from the bottom here to the centroid, is going to be 52.9 millimeters. And just for the purposes of this video, we're just going to round that up to 53 millimeters, just to keep our equation in our calculation a little bit cleaner in the next section. So the next part, we need to find the moment of inertia of this composite shape. Well, we know that the moment of inertia for a rectangle is just over 1 times by 2.5 times by base times the height cubed. So we find this just probably in one of the back pages or the front pages of any mechanics textbook. But the shape that we're looking at here is the composite shape, and the centroids of the individual parts don't line up with the centroidal axis here of the centroid of the whole thing. And you know that we should also draw on our measurement here now that we know that it was 53 millimeters. All right, so now you know, let's write it like this. What we need to do is we need to account for their offset using the parallel axis theorem, and all the parallel axis theorem really does is just, if we basically label this line here the critical axis as our x-axis, then we'll call our moment of a centroidal moment of inertia really for the whole thing is just going to be equal to the sum of all the parts we have, each one's individual moment of inertia. So that would be like this half base times height if we're dealing with rectangles, and then we just add in plus d squared, and d is just the distance from the cross-section centroid to the composite. So for section B, let's draw a straight line. For section B, this is going to be our d, and then for section A, this is going to be our d distance. So we would call this like dA and dB. So if we wanted to expand this out, let's just give ourselves some more space here to work with. Alright, so we should draw those with little i's there. So what we're saying is that we have this equal to the sum of half the base times height cubed plus d squared, and then A is the cross-sectional area of the individual component there. And we can write this out for section A first. All we have is the 112, this time the base times by the height. So we have times 80 millimeters times 20 millimeters cubed. And then we have 80 times by 20, so plus 80 millimeters times 20 times d squared. And dA, well, we have the height up there, which is 70 millimeters, so this is equal to 70 minus the height, 53. So that just gives us the distance there, and that's going to be equal to 17 millimeters. Right, so now we have 17 millimeters squared. So then that's the first area done. So we'll move on to the second area now. So we have this one times by the width is 20 millimeters, its height is 60 millimeters, and this is cubed plus the area of the section, which is 20 millimeters times 60 millimeters times d squared, and the d in this case is going to be equal to, we have 53 minus 30, that's the difference we need if this is 30. If this is 53 and this is 30, the difference there is going to be 23 millimeters. So now we have times 23 millimeters to the power of 2. So when we go and crunch that in our calculator, we get 1.5 millimeters to the power of 4. And often we'll want to write this in units of meters to the power of 4. So then we'll just write this as 1.51 times 10 to the power of minus 9 meters to the 4. And it's also often convenient to put this in units of 10 because that will cancel out with other things later. So we're going to further details on this in the moment of inertia for composite shapes, and this is going to be super important for us moving forwards in other videos and other things where the examples are that we need to calculate maximum tensile or compressive strength in a member that's in pure bending. We'll have this equation where we have the stress is equal to the internal moment times c. The moment of inertia is often, we're not just dealing with square members, we'll have T-shapes or I-shapes and other shapes in this case. So our moment of inertia, we just plug this in, and for calculating c, for example, we would just take the distance of the neutral axis, which passes through the centroid of the whole shape. And in this case, c, the distance to the top of the member, would just give you that distance, which is 80 minus 53 there. And that gives us what would be 27. And then if we wanted to figure out c down here, we would just, as well, that we just take 53. Actually, we'd be able to calculate the problem like this if we were given applied moment. And then we'd be able to calculate the maximum, we know to calculate the maximum tensile and compressive stresses because we know how to calculate the moment of inertia for this composite shape.